All right, for this case study, we're going to talk about tractor brakes. This is one of my favorite projects that I worked on over the years as I was working in drivetrain. This one in particular centered around a significant amount of warranty seen in Europe. If you think about Europe, Europe's very different in their tractor usage. They have different rules relative to over-the-road trucks and semi-tractor trailers versus tractors, so it's more cost-effective from a tax and fuel standpoint for farmers to use their tractors to haul tankers and wagons and slurry and grain using their tractor. The tractors generally in Europe go faster than they do in the US. Some go as high as 60 kilometers per hour. And in that process, they use their brakes a lot. And so in this particular instance, I had the opportunity to get involved in the current product improvement activity around this tractor that's sold in Europe. And in that, one of the things that came up was high brake warranty and high brake part sales, and that was creating customer dissatisfaction. The brakes are actually wet brakes, and they're inside the axle near the differential in the center of the axle. To replace or service the brakes, you have to pull the axle off the tractor, replace the brakes, and it's significant downtime, significant cost for the customer, and that really hurts their bottom line. So the goal of this activity was to understand what was causing the failure and come up with a solution that could get us as close to lifetime brakes, which would be close to 10,000 hours of operation for the vehicle a year. Process, we went through and did a thorough investigation, and that started with doing some initial testing, going through and looking at the failed parts that were coming back from the field and assessing what might be the different issues. In the process of doing that work, there were multiple issues identified. One was that the brake disc was not getting uniform pressure when it was being force was building up on the outside, causing it to be overstressed and tear up the material. So through that process, we went through and actually developed a methodology to be able to estimate how much oil flow was going through the brake disc as the brake was being applied. This has oil grooves in it that allow oil to pass between the piston and the backing plate and the brake disc, and that takes the heat out, and that's what allows it to be a for-life brake. And in that process, we were able to identify that there wasn't sufficient oil to fill up all the grooves, and we were actually getting air contacting. It doesn't transfer heat very well. So we actually developed an analytical tool that allowed us to optimize the oil flow, groove geometry, so that the grooves would fill within fractions of a second, because braking can happen instantaneously, and sometimes it might last for 2 seconds, sometimes it might last for 30 seconds. We want to make sure that it's contacting the disc and pulling that heat away, and so we developed a unique tool that allowed us to optimize that. And then once we had that under control, we were able to address the deflection issue, actually did finite element analysis to understand the deflections, and then optimize the design to compensate those deflections by adding taper into the brake disc. This allowed us to fix the problem with no increase in cost. Solution, because the parts cost us, there was no change in cost, but what it did is it substantially reduced warranty, much so that warranty parts and parts sales after warranty dropped by more than 80%.
If you're seeking expert engineering support and insights, follow us on LinkedIn, Instagram, and Facebook to stay updated with our latest innovations and services.